أهلا وسهلا. Good evening. الساعة 5 and let's start. Before we start with the lecture, let me just share the most recent update I did on the e-learning, and I'm not sure if you guys paid attention. Anybody got any notification from e-learning about anything new?
لا دكتور بصراحة ما وصل شيء.
طيب اوكي. بس
لا دكتور.
before that, remember انه I post the recordings دائما, okay? And the recordings I put them على الشانل تاعت اليوتيوب تاعت my PSUT, okay? المفروض بتشوفوهم يعني. و I put them كلهم في list so you can find them. وبرضه موجود اللينك here. شوفوا, in the discussion forum I posted a new discussion forum topic اسمه research topic first status update. هذا I posted it.
بس تشير السكرين بعد اذنك. سوري.
اوكي ثانك يو. مليح اللي قلت لي بكير. Yes, sure. I should share the screen. Where is the? I thought I was sharing. Share the screen. Yes. So I was in the e-learning, and I wanted to show. You see that I post after each lecture. I post in the schedule here. I post here in the schedule, class schedule, lecture by lecture, breakdown of the topics we cover, the planned that I was planning to cover, what we actually covered. Okay, sometimes the plan moves from a lecture to another, and then the link to the lecture on that day. Okay, so كل يوم بيوم, the link to the lecture video at that day and to the presentation that I used in the lecture. تمام? So that's in the class schedule. At the end, there is a discussion forum, as I showed you last time, and you are free to post any topic you want to discuss with each other. But I posted something last Thursday, a new topic in the discussion forum, and here responding to this thread is mandatory for everybody. It's about the research topic. I need your first status update. This is read the write-up I wrote here, please, and then you reply. Okay, you reply, so I see your name and you reply on what I asked you to for here, right? So what I want, in a nutshell, what did you do so far for the research topic? Did you team up with anybody yet? Are you able to find partners? You want to work alone? Do you find a partner? You don't want a partner? If you want a partner and you don't, you didn't find somebody yet, you can use this discussion forum because you can read the threads from everybody else and see who found somebody and who did not find anybody, and you can communicate with each other, okay, to team up if you want. Then if you did you find the topic? What are you doing? So this is the first status update, and consider it as an assignment, okay? Everything related to the research topic, everything we do until we get to the final deliverable from the research topic is going to count, okay? So please respond to this discussion forum thread. تمام? Great. So I expect, and I put a due date. Sorry, I put a due date. But I read what others say, right? You can subscribe here, and you will start getting notifications on any update, any new post, and read what others do. I want this by March 10th. Okay. By Wednesday, Thursday. خلاص, I'm flexible شوي. And I posted it لأني الخميس الماضي. So try to do it within 2-3 days. ماشي? يعني مش إشي بده يعني okay just يعني يعني as easy as that. بس I just want update. okay اسهل ما نودي لبعض ايميل او زي نحكي خلاص just write what you did. Okay, in today's lecture, last time we talked about the embedded computers, covered the remaining issues from the hardware. We covered the processor, the program memory, data memory, I/O interfaces, interfacing with memory. Today, we're starting with software. Okay, now we're starting to move towards software. So I believe these are the main topics that we're going to cover: computer software, memory operations. We talked about this maybe, but just to formalize it, program execution as well. And then we start with the HCS12 hardware. Okay. So I'm still in the first set of slides that I already posted on e-learning. And we are at slide 18, computer software. So we started with hardware. So computers are hardware and software, basically, right? Hardware and software. Now we're talking about software. So every program needs to be told what to do, right? It doesn't, I'm sorry, every computer needs to be told what to do. It doesn't know what to do. It's just a pieces of transistors, basically, gates, let's say, higher level. So it needs a program. The things you want the computer to do is a program, okay? And a program is a sequence of instructions. An instruction, go right, do this, then do this. A group of instructions that all together make a meaningful task, okay? Basically, when we saw the processor in one of our early lectures, we saw that a processor understands a one, oops, okay, this has to go up in, okay, oh, a one, a zero, a one, a 1 0, and then you get an output, right? It's a group of zeros and ones, and the control unit, when it brings the instruction from the program memory, it decodes it and sends every line to the proper line to be implemented. And by the way, so I just remembered something. When we discussed I was revising the recording that day, and I saw that we missed something here. When we were discussing the subtract is a 0 1. So when you put a 0 1, 0 1 compared to 0 1 is 1. Is 1, and they match, right? So to this, the 1 propagates to this multiplexer. So we have a 1 here on the select line, a 1 here on the select line, and a 0 1 will select this this input of the multiplexer to become the output, which is the output of the adder. The adder will add here, in this case, A, right? And Y will be, since this is a 1, will be B complement, the 1's complement of B. And this is another 1 at this multiplexer. So a 1 will pass, okay? So you're adding A, you're adding A plus 1's complement of B plus 1, right? 1's complement of B plus 1 is the 2's complement. 2's complement. And the 2's complement, whenever you add it to another number, you're subtracting it, basically. It's not, ماشي? And last time, I saw that what I spoke in the recording that A plus 1's complement is subtraction. No, A plus 1's complement plus 1 is subtraction, okay? A plus 2's complement is the subtraction. This is a correction, but anyways, you saw that as a group of zeros and ones will make something meaningful. These come from the instructions. Okay, so a group of zeros and ones is called the machine language. Okay, so an instruction Instruction is to do one thing. Instruction, only one thing. An instruction is a group, a sequence of binary digits. One instruction is a sequence of binary digits, zeros and ones. So this is one instruction, this is a second instruction, this is a third instruction. A sequence of instructions, okay, make up a program. Tamam? What do these zeros and ones do? Only the hardware understands that, and it is tightly coupled and tied to the hardware. Okay, so if a hardware changes, a select line changes, then the instruction should change. Okay, the hardware understands what this is. Okay, this is very difficult for us to understand. I don't know what these zeros and ones mean personally as a human, but the machine understands them. So as a higher level, so if you want to call this level 0, okay, the machine language level 0, which is the lowest level that talks with the hardware. There is a level 1 language, okay, is the assembly language. So instead of saying 1001, I want to call this add. Instead of saying 1010, I want to call it subtract. And when you write your program, you write an add and you write a subtract. Okay, this is called assembly language. Most of you are familiar with assembly. You took microprocessors, assembly language, and this is the assembly language. You write a group of some words that are close to English type of words. Okay, then there is something called an assembler. Assembler. This is a program that translates from these English letters or words into zeros and ones, right? An assembler is just a direct interpreter. It's like a lookup table. Wherever you see ADD, replace it with 1001. Wherever you see subtract, replace it with 1010. So intelligence here is minimal, okay? So it's easier for humans to remember words like this, add or subtract, or add B and A, or add or decrement A. It's easier than remembering zeros and ones. Okay? So this is the assembly language. This is the meaning of assembly language. This is a low-level language, and it is machine dependent. It depends on the hardware. For example, this machine language, this machine instruction, we call it instruction. This part of the instruction, they call it mnemonic. Okay. It means, of course, you should have an instruction set table for every hardware. This is add B with A. Then this means that there should be something called B and something called A, and the contents of these two should be added, and the result should be stored somewhere. Who decides where this is going to be stored? Again, the hardware. Okay. Decrement A. So there should be an A. We call it the operand, the thing that we're going to perform the operation on. We're going to go and decrement it by 1, subtract a 1 from it, and store the result in the same place. Okay. So the instruction is dependent on the assembly instructions are dependent on the machine itself, because the operands perform their operations. The mnemonic, the machine instruction, perform their operation on something we call operands. The operands are the numbers that you're gonna deal with, either add, subtract, increment, decrement, whatever. Okay, we call them operands. This is assembly, and everybody is familiar to assembly. Anybody here did not ever deal with any assembly language? I don't expect so, because in the first meeting I think microprocessors is a prerequisite. Everybody is checked against this. So assembly is an option. As an assembly language is something we should know about. Learning as assembly language. I was reading an article today about people asking, what is the best microcontroller to use in teaching an embedded systems class? Well, this depends on the purpose of the class. What do you want to learn from the class? You just want to learn to make an application and just use it, or you want to understand basic knowledge and then build on it and use it for application, etc. So I'm one of the believers that assembly language will help you understand the underneath hardware and give you the bigger picture. But I'm not gonna spend a lot of time here. Okay, we're gonna start with assembly. We're gonna write assembly for our hardware to be able to see the zeros and ones when they're in memory, when they move to the processor, when they go to the registers, everything. We're gonna be able to track them to understand how the microcontroller works. Then I'm gonna jump to a high-level language. In this case, it's gonna be, in our case, we're going to use C language. Okay. So a high-level language is a language that is higher level than assembly. It is similar to English, and it's not best words. ABA. What is ABA? Okay, closer to add B to A, but you can still find something closer. Okay, say A plus B and store it in A. That will be easier, right? Closer to English. So it's a higher level. To be able to convert or translate a high-level language into a machine language, you will need something called a compiler. A compiler. And this is a whole topic, standalone. Needs a class to teach it. What is a compiler? How does a compiler work? How does a compiler optimize and generate the best machine code, etc. Nevertheless, so when we were dealing with assembly, we talked about an assembler. The assembler converts from assembly to machine language. There is a direct translation table between each assembly instruction and its machine language equivalent. While a compiler has to be smarter, because a line of code in a high-level language could probably need to be translated into 2 assembly instructions, 3 assembly instructions, 4, 5, a for loop, for example. It's much more complicated, needs more intelligence. A compiler does this, okay? So whatever translates from a program written in a high-level language to machine language is called a compiler. And it's a program, a piece of software, a program, okay? And I expect that these things are familiar so far. So when you studied, what is the programming language you learned in your undergrad? Mostly
assembly واخذنا شوي C++.
Right? I think every student in Jordan has to take a programming language, صح?
Yeah, sure.
Yes, correct.
C, I think C, it was C, if I remember well, C or C++, and even humanities, they take Visual Basic, right? So,
For me, I remember, sorry, we started with Fortran, I remember. Then we took C++.
Until old-timer Fortran 77, huh?
Yes.
Okay. Yeah, we don't wanna okay. I don't want to tell you what I learned.
Yeah.
But okay. Yeah. Fortran, Pascal, C, C++, Java, all these are high-level languages, right? And they need compilers to translate into a lower language. The compiler, I think at my time we used to use Borland C, or what was that other compiler? There were several compilers, but I think today they use the Visual Studio, right? Development environment, and it has a compiler in it where you can program in C, right? Visual Studio. Yeah. Okay, so
الانتربتر تبع البايثون بيفرق عن الكومبايلر صح؟
okay, يعني yes,
بيتحول
yes.
لكومبايلر بعدين لا.
Sometimes in some languages you have a virtual machine in the middle, like in Java, JVM, Java virtual machine, because to make the language machine independent. For example, in C, we're going to be able to talk with the hardware. And sometimes if you move to another hardware, you may need to change some stuff. For example, an integer on a certain hardware is a 16-bit, why it could be a different size at a different hardware. Hardware dependent. Some programming languages like Java, for example, they have another layer in the middle, Java virtual machine, for example, where it makes what you write independent of the machine. So the virtual machine depends on the machine, but the language Java, wherever you go, is the same. I expect, I'm not very deep in Python. I know the language high level, but I don't know what does it use. But yes, there are different approaches. Anyways, speaking of compilers and C language, and again, I read this article in IEEE, what's that, IEEE magazine, monthly, Spectrum. I once read the full article about C and people talking about C. Is C obsolete? Is C gonna end? Is C an up-to-date language, or is it outdated? What's the thing? And the claim was, no, C is not outdated. C is gonna stay for a long time as a programming language that a lot of industries still rely on, and it is really hard to replace, as it is a high-level language, yet it can talk with the very low-level hardware. Okay, it has a lot of capabilities, and coming from in the industry, C is still dominant. Okay, this is my experience.
ودكتور عشان السرعة أتوقع صح؟
Well, when you talk with the hardware directly, yeah, يعني
أنا مرت علي ماشين مكتوبة assembly كانت blowing machine.
Maybe, yeah, you sometimes to optimize, yeah, you go lower than the high-level language. You optimize it. Maybe you can do some better optimization than the machine. Yeah. Okay. So when we talk about a high-level language, there is a compiler. Now, compilers are two types: native compilers and cross compilers. And it's in front of you on the screen, but does anybody have a quick idea what is a native compiler, what is a cross compiler? Without reading. تفضل مصطفى.
نحكي عن خلينا نحكي نفس اللانجوج.
Yeah.
هذا بيكون فيها لوكال، هو اصلا الكومبايلر. ممكن الكروس بين لانجوج ولانجوج ثانيه مثلا.
اوكي.
هيك بتصور.
يعني you're very close to the idea, however just replace a language with hardware يعني
او hardware.
Yes, hardware. So a native compiler generates high-level language into machine code. طيب. This is common between both. But where is this machine code going to run? And where is this high-level language compiler running that is going to generate the machine code? Yani, let me give you an example. In your C class, in your undergrad, you wrote C code using Visual Studio, Microsoft Visual Studio, and you over there you wrote a .c file and you built it and you generated code, right?
تمام.
Where did that code run?
الهاردوير دايركت اتوقع.
On the same computer, on the same laptop that was running the compiler. صح? So the compiler is running on a processor اللي هي الانتل processor of your laptop. Generated machine code to run on the same processor. واضح؟ So I'm programming on this laptop. I'm writing code. I hit the build button. I generated code, and I'm gonna run the code on the same machine that is running the compiler. We call this a native compiler. So it generates machine code for the same processor it is running on. Okay? While a cross compiler, no, it's different. I want to write machine code to run on this microcontroller, the HCS12. But you know, this processor here, I don't have enough space to install a compiler. I don't have an interface to a screen, to a keyboard and everything. So I cannot directly go write my program here on this hardware. I write it using a development environment, like the one I told you to install last time. For example, Code Warrior for the HCS12, Micro C, MP Lab for PIC, whatever. Okay, you have a development environment where you have a compiler as part of it, and that compiler will generate code. So the compiler is running on the laptop, but it's gonna generate machine code to run on
different
the microcontroller. Okay. So it's generating machine code for a different hardware than the one it's running on. We call it a cross compiler. So لما انتوا تعلمتوا, when you learned your first programming language in a programming class, you most likely wrote a program on the laptop and you ran it on the laptop. So the compiler that did this is a native compiler. It was running on a processor, generated machine code to run on the same processor. In this class, we're going to use a cross compiler. We're going to write our code on the laptop, on the processor. My Core i7 processor from Intel is going to generate machine code to run on the HCS12 or on the Arduino, on a different hardware. We call this a cross compiler. Okay? Whatever. Okay, and the program you write, your code, we call it the source code. The compiler compiles it and generates an output. Okay, the output of the compiler deliverable is called the object code. The object code that will be used to run on the target. This is a simple example of, this is the source code that you can write in your compiler. We're going to talk about these later. ORG origin 2000. So start at address 2000. Write an instruction called load accumulator A with 1000. Add to A 1001. Add to A 1002. Store accumulator A at 1000, or let's say 1100 hex, and then end this assembly program. This is an assembly program. The assembler will convert this to this machine code. The machine code for LDAA 1000 is B6 1000. Add A 1001 is BB 1001. So, and this B6 1000 starts at address this is program memory address, program memory address 2000, because I told it, and I'm going to explain later on what is org 2000. So start your program at address 2000 in the program memory. Assembler, you wrote LDAA 1000. It converted this LDAA 1000 to B6 1000. Okay, so this is going to take this and go to program memory, address 2000, and this next program memory address, this is hex, the $ is hex, 2001, then $2002, then $2003, and each one of these will take 8-bit, for example. So the way this will be stored as B6, then the 1000, 1000, ماشي. Then at 2002, like 0, 1, 0, 1, 2, so 2 already 0, 0, صح? Then at 2003 comes the next instruction, which is the add a 1001 BB 1001. So this instruction takes how many bytes in hex? 1, 2, 3. This took 3 bytes as well, right? 3 bytes. 3 bytes means 3 memory locations. So if you start at address 2000, 2001, 2002, the next instruction will start at 2003. It's 3 bytes, 2003, 2004, 2005. Then this next instruction comes at 2006. Anyways, what does this? What does translate the source code to a machine code, and every byte part of this machine code, where does it go in the program memory? What does this? The assembler. ماشي. The assembler. So this is about the programming this computer software, okay? So lowest level machine language, higher level assembly language, higher level high level language, and then I'm gonna come to a next level in one dedicated lecture, model-based software development, where you basically don't program, you don't write code, you draw code. And this intersects with software design. And I'm going to come to that piece when we talk about software design.
زي الماتلاب دكتور.
زي MATLAB Simulink.
Yeah.
Okay. طيب. Or Tinkercad or VI. What is that National Instruments thing? VI. LabVIEW. Come on. So there are several choices that you can choose. Speaking about memory, we talked that the microprocessor talks through a system bus with program memory. The system bus is first address bus, second data bus, third control bus, right? Control lines. And the memory is program memory, and data memory, right? Data could be volatile or non-volatile. So you may have RAM, a type of RAM, and E² PROM. ماشي. Program memory is usually flash memory. ماشي. Flash memory. And we talked about this. And we went even lower level detail how to interface it. So you can read from memory, you can write from memory. We talked about these. Okay, there's one important thing when we talk about how about when we read and write to memory, we need to be consistent. There is a convention called Big Endian and Little Endian. Okay, so when you store something in memory, so let's say this is memory, and you have address 1000 and address 1001 ماشي and you want to store this number مثلا 12AC in this memory. 12AC is how many bits? This is hex.
32
ولا 16
لا سوري 16 صح
16 bit.
Yes.
While every location here is 8 bit, for example. So how will you save these 16 bit in 8 bit memory locations? You will need to split them into bytes. طيب. So the AC لحال will 1 2 separate, right? So you store the AC, then you store the 1 2. The question is, where do I store the AC? Do I store the AC here? AC hexadecimal, hexadecimal, and then the 1 2 here, or the 1 2 here and the AC here? This is a question.
الأولى دكتور.
حسب big ولا little بدك.
Okay, thank you. It doesn't matter actually where I store them. It matters that when I store them and then read them back again, I should read them in the same order, صح؟ يعني to keep it meaningful. ما بصير. I cannot store AC first and assume that this is my lower byte first, then the higher byte second. Then when I read them, I assume that what I read first is the higher byte and what I read second is the lower byte. In this case, you'll get a wrong number, right? You'll get an AC12. صح? So what's important here is how you store them. The read cycle should follow the same convention. So here, there are two conventions, Little Endian and Big Endian. When you dealt with Intel, most of you learned Intel microprocessors. Intel uses Little Endian, okay? Little Endian means that you store the lower byte in the lower memory location, the memory location with the lower address, and the higher byte in the higher memory location. This is Little Endian. However, Big Endian, lower byte goes to higher location and higher byte goes to lower location. Lower يعني الأدرس الأقل, the smaller address. So 1000 is smaller than the 1001. طيب. So the low byte, this is the low byte and this is the high byte. The low byte goes to the high memory location. The high byte goes to the low memory location. This is Big Endian. Big Endian. So this one is big. This one is little Endian. It's a convention.
دكتور بصير سؤال.
Yes, تفضل شادي.
طب بالبيج هلا ايش بصير يعني للكاونتر؟ بيكون هو بيأشر على الادرس الاكثر وبصير له ديكريمنت لما يصير بده يقرا، بالعكس يعني عكس الليتل انديان. احنا كنا بنعرف انه على الادرس وبيمشي على اللي بعده، بزيد الكاونتر اللي بيأشر على اللوكيشن بده ياخذ منه.
Okay. Thank you, Shadi. I'm going to come into more details in this, but a very general answer. We need to differentiate between program memory and data memory. طيب. The program memory is where you have to program the ones and zeros, and you have a program counter and moving sequentially. طيب. The data memory is the memory where you store where you want if you know the address. طيب. And it has its pointers. In both ways, the same convention is followed in our hardware. So either program memory or data memory, we're using the Big Endian. And whenever you store, if you say مثلا move, we're going to come to that. There are some things called addressing modes, and when we deal with the instructions and the addressing modes. But when you want to say store a 16-bit number in a memory location address 1000, that means you are going to use 1000 and 1001. طيب. Because 16-bit cannot fit in one memory location, because the one memory location is 8-bit. So you're going to use two locations for sure. The two locations are the location that you provided its address and the following one. If it's a 32-bit, then you're going to use 4 locations: 1000, 1001, 1002, 1003. And whatever comes after is going to come after that. And then if I store another 16-bit or 8-bit, it's going to come at address what? 1002. ماشي? So it's going to follow. And I'm going to come into the details of this when we go and talk about the addressing modes. ماشي? The thing that keeps incrementing sequentially is called the program counter. It cares about the program only in the program memory. And it increments to point to the next instruction, مش next location, here in our case, to the next instruction, not the next location. يعني بمعنى إذا عندك, if you have an instruction 3 memory locations, when the 3 memory locations are fetched, decoded, and are to be executed, the program counter will increment 3 and point to the next instruction to be executed. Okay, not increment 1 location, 3 locations. يعني to point to a next instruction. طيب, big Indian, little Indian. Understood what it is? So here we're using big Indian. بمعنى whenever I tell you go store any word or any 16-bit, you look at the low byte and the high byte. This is the low address and this is the high address if we count from up to down. So this is address 1000, this is address 1001, 1002. So whatever comes upper is lower address. So in the big Indian, the low goes to the high location, the high goes to the lower location. This is big Indian. We just need to remember this. It is the opposite of Intel. طيب. Program execution, we talked about this. Luckily, we were not wasting time. We were arranging the topics. Program execution, you have program memory. We talked about this. We have a program counter, always pointing to the next instruction to be executed. شرحت هذا الحكي صح? If you remember, right? Do you guys remember ولا أنا ناسي ولا
لا حكيت
دكتور.
Okay. Okay. So there is program memory, and you have your instructions here. The machine code that came from the assembler, the compiler, whatever, hexadecimal numbers. مثلا اللي شفناه قبل شوي B61000 مثلا. Now when this is an instruction and add whatever, it is fetched, the 3 bytes are fetched طيب, to the instruction register, decoded over there. Before getting executed, the program counter will increment and point to the next instruction. The next instruction will come here after the 3 bytes. Okay, so the program counter will increment 1, 2, 3. ماشي? Okay. طيب. Where is the first place when you power up your computer on power on? If I get the power source here and connect it, the program counter is a register at the end of the day. Is a register and has contents, and the contents is the address of the memory location where the thing the instruction it's going to execute is stored in it. So when you first power on your hardware, where does the program counter go and point?
Beginning of 0.
No, it skips some addresses because there was a power-up sequence at first.
Okay, if you have a bootloader, تمام عمر. But where should it point? يعني Omar, when you studied the PIC microcontroller, when you first powered up your microcontroller, where did the program counter, or sometimes they call it instruction pointer or program counter, where did it go point? To what address?
ممكن دكتور في ديفولت ادرس اللي هو الفيرست ادرس بالميموري.
Of course there is a default, but in the PIC, and I'm asking Omar because he studied PIC in his undergrad.
I'm sorry, I don't recall actually.
Address 0, if you remember. Right? Whenever you power up your controller or reset it, when you hit the reset button, the program counter always goes to address 0 in the PIC, the 16F877A, the one you studied. Whenever an interrupt happens, the program counter goes and points to address 0004. This is in the PIC. يعني fixed address. We call this the reset vector. We call this the interrupt vector. So whenever you power up your computer, guys, there is a register called program counter that has to point to any instruction, and then the control unit has to fetch that instruction and execute it. Okay, and send it for execution. What is the first instruction? It should be somewhere that the hardware knows. ماشي? And this, what is the something? What is the address? Is it fixed or not? This depends on the hardware. For some hardware زي البيك مثلا والاتمل وال8051, the address is fixed location, and مثلا في البيك address 0. Okay, whenever you power up بتوصلت له power, the program counter will reset, يعني بصير قيمتها 0, which means it points to address 0. So the program counter will point to address 0 in memory. The instruction you have here will be fetched to and executed. تمام? So whatever now we're talking about, we're dealing with hardware level. We need to know where we're gonna write our program, at what address. طيب? And we need to make sure that the first instruction of the program we're gonna write is written in that reset vector, in that location where the program counter will point to when a reset happens. When does a reset happen? A reset happens if you do a manual reset by pushing a reset button, or a power on reset. Okay, a power on reset means whenever you power on a controller, what's gonna start executing first? There should be a first. So to make that first thing happen, you need to reset. So there's a detection circuit. Whenever a rising edge is detected on the power, it will cause the controller to reset, which means clear the program counter if it's address 0, for example, and make it point to the first instruction at address 0. In other microcontrollers, this address is not fixed, but the address is stored at a known location. So you go fetch the address from a fixed location. ماشي? So we have a vector, a location where you have an address that is pointing, or the value of that address, the content, you have an address that has a number. This number is the address of where your first program instruction is at. And we're gonna actually look at it and see it. Okay, we're gonna look at these address vectors. So the question now, the program counter points to instruction. طيب بس the first time you power up, what is the instruction? This is decided by the reset vector. We call it the reset vector. Reset vector. Sometimes this is fixed. You don't need a vector. خلاص, it's always 0. Sometimes أنا بغطي على الشاشة كأني غطيت يعني. Okay. Sometimes it's not fixed. The reset, يعني where you should go point to is well known in some place. Okay, so let's say address 1000. Whatever is here, مثلا, you want the program counter to start at address 2000, you write a 2000 here. You want to start at address 3000, you write a 3000 here. طيب. So this is fixed, but you can change the start address where the program counter will point at. But there should be a location known where to start at. And something has to happen when you first power on your controller. to make the program counter go reset to that default value, to always start the program at a certain point. Is this one clear?
تمام.
Okay. Then the program counter afterwards starts incrementing. So you pointed to the first instruction in the program. مثلا you write a program to control the climate in this room. So your program will start as initialize the registers, initial values of all the variables, the registers, etc. Then read the temperature sensor, convert it to, you read the voltage, convert it to temperature. Then you read the set point by the user from the remote control or whatever. Then you compare if you need to turn on the compressor, then or off, and so on. You keep doing things, but there was something you had to do first. The first thing, okay, when you power up. Then the program counter will start incrementing. Next instruction, next instruction, next instruction, next instruction, okay? So this increments, the program counter, the PC increments to point always to the next instruction to be executed. The next instruction could be in the next memory location, or could be in after 2 following memory locations or 3 following memory locations, depending on the instruction size. And the instruction size برضو varies from a controller to controller. And some hardware like the PIC مثلا, instruction size is all in the PIC 16F مثلا, the instruction size is always قديش 13-bit or 14-bit, I forgot the number. It's always in one memory location. The program memory is always fixed, 14-bit, I think 14-bit. You just get it once, and the program counter increments to the next following, +1 يعني, only +1. While in HCS12, the instruction size could be 2 bytes, 3 bytes, 4 bytes. So the program counter would probably need to increment by 1 or by 2 or by 3 or by 4. What decides this? The control unit. When it fetches the instruction, it knows its size. It knows its size. Then it decides how much it should increment the program counter. So this is the normal operation of the program counter. But in some circumstances, the program counter could be redirected through a jump. An unconditional branching instruction. In PIC, there was no jump, there was a go to. So you tell the program counter, go to address 3000 program memory. Go execute the instruction at address 3000. مثلا. Go to or jump to this address. Unconditional, just go there and execute whatever is there. Or it could be conditional. If this is greater than this, then go here, else don't go. Yeah, okay, that's how you do if conditions. And we're going to discuss this later on. Come on. A program counter circuit could look like this, a D flip-flop. And you know a D flip-flop, right? A D flip-flop, whatever is on the input, whenever you get a clock, a rising edge in this case, the output will pass through to the output. The input will pass and go propagate to the output. Whenever you get the rising edge, so this is edge trigger flip-flop. Whenever you write, there are set and reset, 0, and it's active low, a 0. A set, if you write a 0 here, you get a 1 here, regardless of the input. If you put a reset here, you get a 0 here, regardless of the input. So if you use this flip-flop in this hardware circuit, this is just a simple block diagram of a program counter circuit. Every time you get a clock from the clock source, مثلا oscillator in our case, and you powered on, when you first power on your controller, power on, وصلت كهرباء, you'll get a rising edge. There is a logic that detects this. It would cause a reset. So the address will become a 0. The output of the D flip-flop is Q, right? So this will become a 0. ماشي? Okay. A 0 will pass, add with usually no offset, everything is zeros. So you start with address 0. So the program counter points to address 0 مثلا. Or this could be loaded from somewhere else, preloaded. طيب, اجت another clock, another clock, whatever on the input is gonna propagate to the outputs. So we had a 0 here, is going to pass 0. There is no branch, so here is 0, right? So a 1 added to a 0 is a 1, and there is no jump. This is 0. So you pass the 1 is here, and it's going to propagate here. On the next cycle, the 1 is going to, this is going to happen again, 2, 3. It keeps incrementing. But the amount of increment here is 1. But this is just an example. In our real case, in HCS12, this could work. This directly maps to the program counter in the PIC method. But in the HCS12 here, what you add here is not always 1. Okay, sometimes you add a 2, you add a 3. So there should be a logic here to decide how much you're going to increment. طيب. If you get to an instruction, the instruction says go to address X or address 3000, jump to 3000. So the 3000 will come here. This is the target. Jump will be 1. So whatever is here is going to pass on the clock next rising edge. This is going to be the output of this is the program counter. يعني هنا, this is the program counter. You're going to get the 3000. Okay. It's going to overwrite the add, whatever. And whatever you add is not, this is not important. If you have a jump, you're going to take this input, not the adder output. Just a simple block diagram of program counter. Okay. And we talked about this. Now, the book proceeds as follows. Now, this is for beginners who never dealt with a processor. It wants to introduce you to how processors work. For us, I surveyed everybody when we started. Everybody had a kind of microprocessor course before they started. So here in the book, they imagine a processor called X, a processor X, and put rules and just to explain to beginners what is a processor, how it works, what is a memory address, what is a addressing mode, what is an instruction. So for us, this part we're gonna skip it because we all had a prerequisite course in microprocessor. So I'm gonna jump till this start. So to remember in the slides, من هون, whenever we start, when you see the processor X, you jump until you get to this star. We're gonna directly deal with our processor, the HCS12 processor. ماشي. طيب, let's begin with HCS12. Now we begin with the true hardware that we're gonna deal with for the rest of the semester. We're dealing with a processor called HCS12. And again, we need to understand, well, MCU, what is MCU? MCU is Microcontroller. M micro, C controller unit. طيب. MCU, microcontroller unit. We're talking about the microcontroller, which includes a processor inside, memory, program memory, data memory, peripherals. تمام? And we're going to use this microcontroller to build bigger embedded systems with all the interfaces we need, with all the sensors and actuators we need, with all the communication we need, etc. Okay? And when we design the bigger system, how we start thinking of the system, how we design it, how we put the requirements, how do we translate the requirements into, at the end of the day, to code, embedded software code, with all the constraints that we have with embedded controllers, okay, that you don't have unlimited program space, unlimited clock frequency, and etc. And produce an embedded computing system that does something specific. So this is the purpose. So to be able to do that, we need to learn about this MCU, this microcontroller. Now, in your real life, when you go outside in the industry, go wherever you want to control to build an embedded system, one piece of that embedded system or that control system or whatever is the microcontroller unit. We're learning the HCS12 on its lower level. We're going to go to a very high level in it. Okay. Yani we're going to start from machine language. We're going to cover high level language. We're going to cover model based control even and design. Mashi? This will make it easier for you later on. Okay, I don't have this. The guys who I want to work for want an Arduino. They want a Raspberry Pi. You're going to just go use it. Usually those things are more popular. They have a lot of available libraries, shared communities that you can just get pieces of code about this, see the application notes of the sensor, of the hardware, and get how to read it. Mashi? But you still need what we're going to learn here, what's going underneath. As a graduate level engineer, you need to know and understand well what happens underneath to be able to solve problems. And I'm going to tell you about a small story. When I used to work with one of a governmental entity, they used to make drones. And in some circumstances, a drone, after flying for a certain time, it always falls. It falls, oh, boom, and you lose hundreds of dollars. For يعني هيك a general user, nobody يعني they let me summarize. يعني they spent a lot of time to try to figure out what the problem is, and the problem is was something يعني very trivial. Any embedded software engineer should think of first before trying to debug other stuff. I'm going to cover these things in coming lectures. But anyways. So this is the importance of dealing with a controller that is available. Its architecture is easy to understand to give us the understanding of how bigger systems work. Okay, the HCS12 microcontroller is a 16-bit microcontroller. It is 16-bit, which means it can deal with operands of size 16-bit. It's an upgrade of something called 68 HC11 MCU microcontroller that was 8-bit. Okay, it's an upgrade. When they upgraded the HC11, they created the HC12. It was not satisfactory in the market. Okay. The HC12 compared to HC11 had the clock speed of 8 megahertz higher. The clock speed was revised in a new architecture that can achieve 25 megahertz bus clock rate. يعني يحط لي خطين تحت bus clock because it's different than the source clock. And I'm going to explain that later. Come on. The revised version that solved the issues it had, the HC12 had, and had this higher bus clock rate was revised, and they started referring to it as the star 12, S12. S12, they put the S next to the HC, so you got the HCS12. Mashi? This is the history, how the HCS12 came. Its main features. The CPU can deal with 16-bit numbers. So it's a 16-bit architecture. طيب. The 3 types of memory here. It has an address space of 64 kilobytes. This can be expanded to 1 meg. شو يعني address space of 64 kilobytes? يعني my address lines are 16 lines. 2 to the power 16 can address 64K locations. 64K يعني 65,536 I think ولا
6 مظبوط دكتور.
36, yes. If I have 2 digits, how many address space do I have? If I am I'm allowed only to use 2 digits. How many numbers can I generate from 2 digits? Binary.
4 numbers.
2 to the 2 equals 4, صح؟ اللي هم 0 0 0 1 1 0 1 1. Oops, 1. Okay. 1 1. Okay. If I have 3 bits, 2 to the 3 equals 8, right? So I can have 8 numbers: 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. صح? So every bit you add, you double the space you had before. صح? When I had 2 bits, I was able to cover 4 locations. When I have 1 bit, I was able to cover 2 locations or 2 numbers. When I have 3 bits, I doubled the 4, it became an 8. صح? I have a 64 kilobyte memory space, which means I have 16-bit address. I'm dealing with 16-bit address that can cover up to 64 kilo locations. And it's called a memory space. So part of it could be used. يعني مثلا من address 0 to address 1000 can be used. من address 1000 to 1500 could be not used. 1501 up to 2000 or 3000 could be used for E square prom. 3000 to 7000 could be used for flash memory, the program. 10,000 to أبصر إيش أسرع. Okay, so you have the space and you use the space accordingly. So it supports 64K, in some cases 1 meg. Okay, 1 meg where you have windows of 64K. So you cover a 64K at a time, you can make, يعني whoever dealt with 8086, remember, إذا anybody here dealt with 86, you used to have segments, صح? Segment, stack segment, program segment, data segment. There was a segment register that you were able to change the 64K address space that you're looking at as a window. In PIC, we used to call it pages. صح? Page number 0, page number 1. Okay. So we're talking about like a sliding window that you can look at a 64K memory space at a certain, at one time. But you can look at another 64K by changing the page. Paging, we call this paging. Anyways, this is the supported memory space, but the actual memory depends on the hardware. So the hardware model we're going to use, the one has مثلا 256 flash memory, right? If you remember last time, 256 when we looked at the block diagram. So the E square prom, it could not have E square prom on it, and it could have up to 4K E square prom used for data memory, but non-volatile data memory. The SRAM اللي هي data memory, volatile data memory. The SRAM could be from 2K up to 14K depending on the memory, the family member. The program memory, يعني شيء هون بحكي لك flash memory. We should be able now خلاص to understand that flash memory is the program memory. Could range from 32K up to 512K. In our particular case, we're using is 256K, 256 program. And you can write instructions with a size up to 256 kilobytes. It has sophisticated timer functions that include input capture, output compare, and PWM. And again, pulse accumulator كمان صحيح 4. Real-time interrupt RTI 5. And a watchdog timer COP. يعني COP, you can remember it as a COP شرطي, but it means computer operating properly. Computer operating properly, يعني الكمبيوتر شغال بشكل صحيح. COP timer, which is in other cases they call it the watchdog timer. What does each of these things mean? I'm gonna talk about every single thing. But looking at many different microcontrollers, the HCS12 is one of the most powerful. Our free-scale controllers are one of the most powerful controllers, and equipped with very important, sophisticated timer functions supported by hardware that can be able to do all these functionalities. So it supports real-timeness. That's one of the secrets why it's heavily used until date in the automotive industry. Okay. Serial communication interfaces. It has different serial. It has a communication interface that enables a controller to talk with another controller serially by sending a bit after a bit, not parallel. Okay. Serial communication interface, asynchronous, SPI, serial peripheral interface, synchronous, that has a common clock between the transmitter and receiver. It has a CAN bus. It is capable of interfacing with a CAN network. And here we're talking with a network of controllers, controller area network, not one-to-one, one-to-many, or many-to-one, etc. And the BDLC is, I forgot what is short for. I forgot. It's a communication thing. I forgot it. Maybe I'll check it next time. Background debugging mode that enables debugging in the background, single stepping, and etc. It has a 10-bit analog to digital converter that can be configured to 10-bit or 8-bit. And also we're going to talk about that. And it supports fuzzy logic functions directly, instructions. These are the main features. We're going to spend a lot of time in each piece of these things. Now, to be able to start with the microcontroller, we need to know, last minute, but let me finish this one. We need to know the registers. The HCS12 has some registers, has a lot of registers. To configure everything here, you need to deal with registers. Some of the registers are CPU registers inside the CPU, and some are I/O registers. The CPU registers, we have accumulators, register A, B, 8-bit, 8-bit, so you can add A with a number. It can be an 8-bit number, okay, an accumulator called B. But both can be combined, A and B, into one single register that you can call D. ماشي كأنه زي بالانتل كان في A low, A high, B low, B high, something like that. و BX بدل هنا D, register D is the 16-bit one. Half of it is 8-bit, another half is 8-bit. There are index registers. قديش ساعة صارت والله
6:15.
طيب أنا بصراحة بديش أشل في كون. So next time we start at the registers, okay, and addressing modes. So thank you for listening, everybody, and interacting. If you have any questions, you can stay till after I stop the recording and we can discuss.